All right, next up we have Shen from Texas A&M. Integrated and spatially resolved interstellar medium properties of galaxies at redshifts 2 to 3. Okay. Okay. Can everyone hear me? Hi, I'm Lucian. Is it closer? Maybe display better. Okay. So today I'm going to talk about integrated and spatial resolved ISM properties of galaxy at redshift 2 to 3. So this is the data is mostly from NGDeep survey, and I want to special thank to Casey and Weda. They helped me a lot on the analysis and everything for this project. And also Nor and Jaslyn, they're not here, but they did a lot for the data reduction. Okay, and so I would like to start from the two key ISM properties. That's the metallicity and ionization parameter. So these are like very important ISM properties that shape the star formation and the feedback. And here I'm showing a plot with O32 ratio as function of R23. So these two are the common tracer for the ionization parameter and metallicity. So here the dots, the histogram here is the SDSS data, and the orange dot here is the MOSDIF sample at redshift 1, 2, 3. And we see that from SDSS to slightly higher redshift galaxy, they're moving in this space, like they're having low metallicity and high ionization parameter. And once we go to with the JWST, we're suddenly observing galaxy at redshift 5 to 10, and this galaxy appear at much higher ionization and low metallicity region. And so as the stellar mass histogram, this is they're much lower stellar mass. And there seems a gap between the intermediate redshift galaxy and high redshift galaxy. So here comes the NGDeep survey. So NGDeep survey is designed to target low mass galaxy at redshift 2 to 3, and this is a perfect filler to the space between the MOSDIF and the high redshift galaxies. In both the metallicity ionization diagram but also the stellar mass diagram. So we extend from down to 10 to the 8 solar mass. And some more details for the NGDeep survey. So this is a cycle 1 program, and we are using parallel observations. So one is near cam imaging that's covered a very deep HST F115 A14 imaging. This is optimized for observing galaxy at redshift of 10 above. And then we also have nearest component that are designed to obtain a key nebula emission lines for a galaxy 10 to the 8 solar mass. And in the final the data set, we have we reach final emission line 5 sigma flux limit down to 10 to the -18th arc per second per centimeter square. And this sample is really a great sample to study the low mass end of mass metallicity and mass ionization parameter relations. And this will give us help to constrain the feedback models. And also we are able to do stochastic star formation rate with the H-alpha emission lines and UV. And also I want to highlight that we could do spatial resolved star formation and SM properties. This is because the design of the NG-deep nearest, we have 4 different position angle. So we can reconstrain the emission line map as shown here. This is the H-alpha emission line maps. And we combine with the this is false color from J's data. And also on the bottom here shows the O2, O3 H-alpha emission line map. Okay, and so I want to focus on the O3-2 ratio here. So for this analysis, we select 49 galaxy at redshift 2 to 3, and we extend down to like 10 to the 8 solar mass. But we for most of the analysis, we say that we complete down to the 10 to the 8.5 solar mass. So all the relations are derived down to this relation, this stellar mass. And then here showing the star formation rate as function of stellar mass, and this is our galaxies, and this is like a star formation rate, star formation main sequence at similar redshift, and we are slightly above the main sequence. This is because our emission line selection. So this is we're slightly higher star formation rate galaxies. And here I'm showing the main result of this paper. So this is O3-2 ratio as function of stellar mass, and all the dots are small dots are the individual galaxies, and color coded by the redshift. And there's also some like triangles, those are upper limits, lower limits. Yeah. And the larger dots are the medium with the purple one is higher redshift, and the purple one is lower redshift at redshift 2, and the orange one is at redshift 3. So the thing we see here is there's a very well correlation, like tight correlation in the O3-2 and mass relations. And when we fit this line, we fit down to the 10 to the 8.5 solar mass, but we see this correlation stay as in much lower stellar mass region. Okay, this is the same plot as before, but we here compare to the galaxy at similar redshift at redshift 2 from most stiff and clear. And those are this like open squares, diamonds, dots, and their end at stellar mass of 10 to the 9 solar mass. So we find consistent result as they showing, but we extend to lower stellar mass. And also we compare to like the green pea, class A, and blueberry galaxies. Those are like much lower stellar mass, but at local universe. So we also see kind of similar like location there as they're located in the similar region as we have. But what we see also is we have a very difference between the SDSS sample. So this is 0.6x. And if we look at O3-2 ratio as function of star formation rate, this is become like even higher, like 1x difference. So the question here is what drives the O3-2 ratio to be higher in high redshift, and also what's drive this O3-2 ratio to be higher in low stellar mass. So first we look at the O3-2 ratio. We continue to look at the integrated part, and this is O3-2 ratio as function of specific star formation rate. And when we plot it, we see like galaxies are normally in the same like relation, including like different like galaxy sample. So this is give us idea that this is suggesting that enhanced star formation activity to drive this O32 ratio to be like higher. And also another question you may want to ask is what's really the O32 ratio are tracing? Because here's a plot showing the O32 ratio as function of ionization parameter. This is from Lisa Cooley photoionization model, and you see this is a very well correlation, but also this is depend on the metallicity. So if we think that the O32 ratio is like dependent on the metallicity, then what we see in the mass O32 ratio relation, that could be just the mass metallicity relation. We know that for a long while. And what we do is we use IZI as a Bayesian code to derive the metallicity and the ionization parameters. So here showing the ionization parameter as function of O32 ratio, and this is metallicity of function of O32 ratio. And we see a very tight correlation here, but this correlation is much like has a large scatter. So we conclude that the O32 ratio is more tightly correlated with the ionization parameters. And for the next part, thanks to the data we have, we could do spatial resolved way. We could study the spatial resolved star formation and O32 ratio, and what's the correlation between that. And what we selected 50 star forming galaxy out of the like almost 150 galaxies, because the PSF of the nearest is we need the resolved galaxies. So this is the sample of the 15 galaxies. The without color, those are galaxy in the whole sample, but they're like low mass, they're small, they're compact, we could not resolve them. So on the top panel, this is showing the O32 ratio, O32 ratio map. And the second panel is the stellar mass map, and the bottom panel is star formation rate map. And these two are derived from the ICD fitting, pixelized ICD fitting. And what I want to point out here is the region that has a high O32 ratio, or the with O32 ratio detected in our map, we also see a very high star formation rate, and the same here. So you can, but this is not correlated with like any stellar mass here, and here is like this region is correlated with this region. So we do statistical way rather than like just looking at the image. And here showing the O32 ratio pixelized pixel by pixel as function of star formation rate density, surface density, and this is equivalent with H alpha. And this also star formation rate is derived by H alpha emission line maps. And we see a positive correlations in the when we bin like the median. So this is suggesting that the resolved O32 ratio are correlated with the star formation rate, surface density, and also equivalent with H alpha. So the equivalent with H alpha is similar it's also a tracer of enhanced star formation rate. So this is the similar as we find in our integrated study that the O32 ratio is correlated with the enhanced star formation rate, star formation activity. And what we did also is to compute this properties, the gradient of these properties. So the gradient, I mean, is like, for example, the O32 gradient is the O32 ratio as function of distance to the galaxy center. So the galaxy center here is defined as the baryon is a baryon center. And what we plot here is the O32 ratio gradient as function of stellar mass gradient, star formation rate gradient, and specific star formation rate gradient. And we see there's no correlation in the stellar mass gradient, but we see like a strong correlation in the star formation rate gradient and specific star formation rate gradient. So this is giving us a same result as I show in the 2D histogram, that the O32 ratio resolved O32 ratio is highly correlated with the star formation rate surface density and enhance the star formation rate activity. Okay. Summary. So we and the NG-deep nearest this is optimized to detect the nebula emission line like H alpha, O3, O2, and even H beta in low mass galaxies down to 10 to the 8 solar mass at redshift between 1 to 4. And we're able to study the ISM properties in this low mass star forming galaxies. And here in this work, particularly did a study on the O32 ratio, and we find a tight negative correlation between the O32 ratio and stellar mass. And we see an elevated O32 ratio at fixed stellar mass and star formation rate compared to redshift 0 galaxies. And we think this the higher O32 ratio is due to the enhanced recent star formation and the higher star formation surface density. And this is seen in both integrated and spatial results.
Thank you, Lou. It's really nice to see this nearest results from NG Deep. That's really beautiful. All right, time for 1 or 2 questions.
This is beautiful data, and I agree with these conclusions. I'm curious, did you look at the ionization parameter versus metallicity? Because we find really interesting and unusual things when we look at it with H2 regions, and it looks like you've got a large sample that you could do this with. And I'd be curious to hear whether you see anti-correlations or scatter plots.
The ionization and the metallicity?
Yeah, ionization parameter versus metallicity.
Yeah. So do you mean in the integrated or in the resolved?
Resolved.
Resolved. Yeah, it's a little bit hard for the metallicity in the resolved map because the H beta is relatively like low, like faint.
Okay.
There's only like 10 galaxies we could do this study. So yeah.
I'd still be curious to know what it looks like in those 10. So let's talk offline.
Yes.
Okay, if we could have Celia come up and get set up, and I'll take another question. There were a whole bunch.
Nice talk. So I'm pretty intrigued by yesterday the simulation results shown by Harry. So it seems like either the physical properties of the galaxy or the turbulence can influence your line ratio by a lot. So do you consider like what kind of the influence that they can have for to interpret your result?
Can you repeat the
physical properties of the galaxy, like the star formations and the turbulence, they can influence the line ratio and presumably also for the O32. And I wonder whether the turbulence so have you like consider? Okay.
Yeah, we didn't consider turbulence and also the only thing I can say is there's a like clumps like this if we look at some high like O32 ratio region, they're also like in the high star formation rate region, and there look like clumps in the galaxy.
Okay, let's thank Lou again and move on to the next talk.